Hello, Mr. Colati here. Today we will be continuing our study of probability by learning a new definition, independent events. Consider this example. You have a game that involves flipping a coin and rolling a dice at the same time. What is the probability of rolling a 1 and flipping heads at the same time? So one way to think about this problem is to draw a sample space diagram. I really like to draw diagrams to help me do word problems. So this is for the question like this, sample space diagram, which we've sort of seen before when we did our first, one of our early lessons in probability. This can be useful to solve the problem. So I'm going to make a table that represents my entire sample space. That is all of the possible answers. So I have, it's 6 by 2. Oh wow, this is very wide table here. So in terms of the die, you have 6 options. 1, 2, 3, 4, 5, 6. And in terms of the coin, you have 2 options, heads or tails. So if I want to map out all of my possibilities, well, it would be this table. You can have heads 1, heads and 2, heads and 3, heads and 4, heads and 5, heads and 6, tails 1, tails 2, tails 3, T4, T5, T6. And you can see from this, we see that the probability of heads and 1, probability of heads and 1 is equal to, well, if you remember, okay, so the only option that's heads and 1 is one option out of my 12 total, so it's 1 in 12. So that's how we solve a question using sample space. Now, the alternative method, which I'm going to show you over here, consider what's the probability of getting heads? Well, you have a coin 50-50, so it's 1 in 2 of getting heads. What's the probability of rolling a 1? Well, there's 6 sides, so it's 1 in 6. So the probability of heads and 1 is the probability of heads times the probability of rolling a 1, or 1 over 2 times 1 over 6 is equal to 1 over 12. Same answer. This is called the product rule. And we like it because it's very quick. It helps us find the probability of what we're going to learn is 2 independent events. You just multiply the probabilities together. It's a lot faster than making a sample space diagram, so we're just going to make a little note about that. Sample space is easy, visual, but slow and not effective for 3 or more events. So yes, the product rule is very quick, but you don't actually see the problem. I like the sample space diagram for a problem I don't understand because it allows me to map out all the options. So don't discount this, and there are a few homework problems where you have to use it. The problem with the sample space diagram is it takes a while, and if you had 3 or more events, it's very difficult to do. Like, what if my game involved flipping a coin, rolling a dice, and rolling a dice with 8 sides. So I had 3 things I was doing. Well, it'd be hard to make a table of that. So sample space diagram can sometimes be useful, but the product rule is quicker and more efficient. So let's just define the product rule here for independent events. The probability of A and B is equal to the probability of A times the probability of B. That is, oops, sorry, there it is. This is my product rule. Now, we should define what we mean by independent events. I mean, this formula only works if the events are independent. And an independent events means that the occurrence of one does not affect the occurrence of the other. So think about two things in your life where one does not affect the other. So for example, let's say, it could be any two things that aren't related. So for example, the classic one I think for students on TTC is paying your TTC fare and the fare inspector is on the bus. Right? So those two things are independent. You pay your fare. It has nothing to do with whether a fare inspector is going to show up or not. What about the fact that it's raining outside and Mr. Colati is late? So the portable is locked. Right, those two things, one doesn't affect the other. The fact that it's raining doesn't mean I'm late, but it sucks for you, right? If it's raining and I'm late, if those two things do happen, well then you're waiting outside in the rain, which isn't great. And you can think of two other things that aren't related, like forgot my lunch, and what's something that's not related to forgetting my lunch? They forgot my lunch and there's a test today. Maybe though they are related. Maybe the fact that you were up all night studying for your test means that you forgot your lunch. That would mean that they're related. But in theory, these two things aren't related. One does not affect the other. I mean, the easiest example is flipping a coin and rolling a dice, right? Those two things do not affect each other. Those are independent events. Maybe I need better examples. Okay, let's do this longer example then. The highest hand in 5-card poker, so this is a card game, is a royal flush. That's when you get an ace, a king, a queen, a jack, and 10 of the same suit. This is like the greatest hand that'll beat anything. You see it all the time in like James Bond movies when they're playing cards. So even though it's very, very rare to get. Consider that you're one card away from a royal flush. So I have the 10, jack, queen, king. I need one more card. If it's an ace of clubs, I would have a royal flush. I would have an unbeatable hand. So I draw a card from the deck. What is the probability that you draw the card needed to win? Well, you guys can think of that. There's one card I need, and there's 52 in my deck. So I have 1 in 52 chance of getting that card. Okay, now. Oh yeah, we're drawing it from a new deck. For all of you saying, oh, I've already drawn 4 cards. Well, no, if I have a brand new deck with 52, the chance of me getting that ace of clubs is 1 in 52. Okay, so let's say you draw a card. It's not the ace. If you replace the card you drew back into the deck and draw a second card, what is the probability that when you draw the second card, that you draw the card you needed to win? Well, it would still be 1 in 52. Right? Because you put the card back in. So I took a card out, put it back in, so I still have 52 options, and I still need one specific card. So this is an example of independent events as well. Because taking the card out the first time doesn't affect, I put it back in, so the probability doesn't change in my deck. This idea, what we often will see in questions, is there's replacement. I've taken the card out, put it back in, so the events are independent. The deck hasn't changed. The other alternative, the flip side to this, is you took out one card, it's not the card you needed. You throw away the card and you drew a second card. What is the probability that you drew the card you needed to win? Well, there's one card you need to win, but there's only 51 options now. The probability of my deck has changed. So this is not independent. These are dependent events. One event impacted the other. The probability changes after removing one card. This lesson is section 6.6, conditional probability. Okay, so that's a different lesson. That is not what we're doing today. Today we're just focused on this much easier thing, independent events. If the events are independent, you can just multiply the probabilities. So finally, let's do an example. 3 green marbles and 2 yellow marbles are placed in a bag. What is the probability of randomly drawing a green marble followed by a yellow marble? And here's the key, assuming that the first marble is replaced, it's put back in. So then the situation is like this. These are 2 independent events. This is put back in the bag. So that is therefore independent events. That's the key word telling me this is independent events. So if you want to find the probability of getting a G green and then a Y, essentially you're saying G and Y. So that would be the probability of G times the probability of Y. The probability of getting a green is, well, there were 3 options out of my 5. The probability of getting a yellow was 2 out of 5. So my total probability is 6 out of 25. The independent events, it's not a too complicated a lesson. Like, it is what it is. You just have to multiply the probabilities. So our homework today is page 82, number 1 to 16, and page 79, number 1 to 5. Right? That's the and symbol. Okay, now what we're going to do now is turn the page, and we're going to do a TOK talk with this interesting probability problem called the birthday problem. It's not just for fun, though. It's not just for TOK's sake. The birthday problem really helps you answer some of the difficult homework questions at the end of today's lesson, at the end of today's I think homework. I think it's page 84. There's a few questions you're going to be able to do that are difficult, but this birthday problem strategy will really help, and I'll keep referring to it. So you should be able to follow along with what I'm going to say here. What are the chances that 2 people in our class have the same birthday? So usually we have about 25 students in the class. What's the probability that 2 people have the same birthday? Usually, you can try this next time you are in a real classroom, but usually the students say it's very low, with 5% chance, 1% chance. But I will tell you, and we're going to prove this, for a group of 23 people, there is a 50% chance that 2 people have the same birthday. Okay, now we're gonna prove this. The way we're gonna prove this is we're gonna actually look at people who don't have the same birthday. But let's start making a few assumptions for this proof. First of all, we're gonna assume that there's no funny business. There's no leap years. There's no twins, etc. Okay? What we're trying to find is the probability of A, where A is the event is 2 people with the same birthday. The same B-day. Okay, like I said, and this is the strategy we're going to employ for some of the homework questions at the very end. instead of trying to find PA, we're going to find, or we're going to look to find PA complement. What is A complement? Well, if A is two people with the same birthday, we're trying to find A complement, which is two people not having the same birthday. Okay, so let's start by saying, let's go around the room. Let's start with the first person in the room. What's the probability that the first person in the class has a unique birthday? Well, if I'm going around the room, the first person I select, the birthday has to be unique because they're the first person I've interviewed. So if they say March 18th, that's that of course no one else has that yet because they're the only person I've asked. So it's always going to be unique. The second, then let's look at the probability. So let's interview the second person in the class. Okay, well this person, for them to have a unique birthday, remember, not having the same birthday. So the first person said March 18th. The second person, the probability that their birthday is not March 18th, there's 364 days left in the year out of 365. So that probability is very high that they're going to have a unique birthday. Okay, let's continue. The probability that the third person has a unique birthday. Well, here now there's two options that have been taken, but there's a 363 over 365. We can keep doing this. I mean, technically the first one, it's 365 over 365. That's why it's 100%. Should we do another one? Let's do one more. The fourth person has a unique birthday. The probability is 362 over 365. Okay, now we were interested in looking at 23 people. So let's continue this process until I get the probability that the 23rd person has a unique birthday. The probability for them would be, okay, the first person, the second person, so I subtract 23 and add 1, so I get 343 divided by 365. Okay, so far we're in agreement, right? So even for the 23rd person, the probability of them having their unique birthday is pretty high. Now, are these independent or dependent events? Does the first person's birthday affect the second person's birthday? Probably not, right? The people in the room, the birthdays are independent. So the probability of not having the same birthday, right? Unique to have, they're all different, they're unique birthdays. It would be, for the first person, it's 365 over 365 times the probability of the second event, which is that the second person has their own birthday, times the third, times et cetera, all the way up to 343 over 365. We can do this because these are all independent events. But one birthday doesn't affect the other. Now, just to make our life a little bit easier, I'm going to factor out 1 over 365. I factor it out how many times? 23 times. And then I'm left with 365 times 364 times 363 times ... all the way to 343. There's a shortcut for this. This is actually 365 factorial over 342 factorial. I mean, you could do the multiplication 23 times yourself, but there's a shortcut. You don't know this yet. You haven't learned this yet, but it's a button on your calculator. But we'll teach you this actually in the next chapter. It's coming. But either way, you can type all these in. So 365 is a button on your calculator. It is, where's mine? It's an exclamation mark. Factorial, I've lost it. Oh, there it is up here, x factorial, so shift. Divided by 342 factorial. Oh, okay, I can't do it with my calculator. You're going to have to do it with a more advanced calculator. But we type all these in into a more advanced calculator, and we get 0.4927. Now, that's the probability of two people not having the same birthday. The probability of people having the same birthday, then, is 1 minus that probability we just found. So I get 1 minus 0.4927, which is 0.5073, which is around 51%. Hey there, look at that. So the probability that two people have the same birthday is 51%. Right? And the way we found this, if you look at the big picture, is we looked at the probability that everyone has a unique birthday. So I multiplied all of these together, and I found that the probability that everyone has a unique birthday is 49%. So then the probability that it's not unique, that there's at least one pair, is 51%. It's like a backwards way of doing the problem. In order to find this one, in order to find something, I have to actually look at the complement. So I show you this method because it's interesting. It's a cool party trick, and you will see in your homework, especially for page 84, number 14 and 15, you have to use this strategy. So it's not like just for fun. There is a point to it. So good luck digesting that. Good luck with the homework, and we will see you next time.